Have you ever wondered how your phone knows it's you, or how a self-driving car can actually see the road? Well, the answer is this incredible story that doesn't start with silicone chips, but with us, with biology. It's the amazing story of how we taught machines to learn by stealing an idea from the most powerful computer on the planet, our own brain. Okay, so let's dive right in. Here's the game plan. We're going to start with the original inspiration, the brain. Then we'll walk through the early days, the big breakthroughs, and a really tough time that followed. After that, we'll see how machines finally learned to fix their own mistakes, which led to the massive AI revolution that is, well, changing everything today. You know, before we even talk about computers, let's talk about you. How do you know what this animal is? Think way back, probably to when you were a little kid. How did you learn to look at this and just know that's a leopard? The way you learned is actually the key to this whole story. Right, so it all started by looking in the mirror. The very first pioneers of AI basically said, hey, why reinvent the wheel? Mother Nature already built the most amazing learning machine ever. So they decided to just, well, steal the blueprint. Think about it. Someone probably showed you a picture, pointed and said, leopard. That word, leopard, is what we call a label. And your brain, without you even trying, started picking out the patterns, the spots, the ears, the color. We call this supervised learning, and it's the exact same idea we use to teach a computer. Simple, right? So the big idea was to literally map the brain's process onto a machine. You see the leopard? That's the input. Your neurons start firing and figuring it out. That's the processing. And when you say, hey, it's a leopard, that's the output. They wanted to build a machine that worked in exactly the same way. And they went deep, I mean really deep, creating a digital version for every little part of a neuron. But here's the most important piece of the puzzle: synapses. In our brains, some connections are stronger than others. They copied this idea and called them weights. A high weight just means that connection is super important for getting the right answer. So the connection for spots is going to have a really high weight when you're trying to identify a leopard. So if you strip away all the fancy terms, an artificial neuron is just a tiny little decision maker. It looks at all the data, spot shape, ear roundness, whatever, and it gives each piece an important score, a weight. Then it just adds it all up and makes a guess. That's it. All right, so with this brilliant idea in hand, these pioneers took their first wobbly steps. The excitement was off the charts, but it very quickly slammed into a wall. And that led to a long, cold period where it felt like the dream was over. So in the 40s and 50s, things were moving fast. We get the first ever mathematical model of a neuron, then the idea that connections get stronger the more you use them, which makes total sense. And it all leads up to 1958 and the perceptron, one of the first real working artificial neural networks. And the perceptron was a huge deal. For the first time, a machine could actually learn. It was like watching a baby take its first step. It was just amazing. But just like a toddler, its view of the world was super simple. It just couldn't handle anything that was even a little bit complex. And this slide shows you the exact problem. The perceptron could only solve problems where you could draw one single straight line to separate the answers. But the real world just isn't that neat and tidy, right? A lot of problems, like this classic example called the XOR problem, just can't be solved with one straight line. It was a fatal flaw. This limitation got put under a microscope in a famous 1969 book. The critique was so brutal, so convincing, that it basically killed the project. Research funding dried up. People lost faith in the whole idea. The excitement just vanished. And the entire field went into a deep freeze that we now call the AI winter. For decades, progress just stopped. But you know, winter doesn't last forever. And a powerful idea was about to be rediscovered. An idea that would fix the perceptron's biggest problem and bring neural networks roaring back to life. The Great Thaw happened because of one incredibly powerful idea. What if the network could teach itself? The answer was an algorithm called backpropagation. It had been around for a while, but in the 1980s, people realized it was the key. It was the thing that would let networks learn from their own mistakes. So how does it work? It's actually super intuitive. First, the network makes a guess. Then, it checks its answer against the correct label. If it's wrong, it figures out how wrong it was, and it sends that error message backwards through the whole system, telling each little neuron, hey, tweak your weights a bit so we do better next time. It's just like a good teacher giving helpful feedback. And just like that, with backpropagation, the single-line limit of the perceptron was shattered. The door was now wide open. Researchers could finally start building much bigger, more complex digital brains, setting the stage for the absolute explosion that was about to happen. So now that these networks could learn from their mistakes, the next step was kind of obvious. If a couple of layers of neurons are good, well, what if we used a lot of layers? It was time to go deep. Deep learning sounds really complex, but the idea is simple. It just means using networks with tons of layers stacked on top of each other. Think about our leopard again. The first layer sees pixels. The next layer puts those pixels together to see edges. The next one sees shapes like spots or ears. And on, until the very last layer puts it all together and says, yep, that's a leopard. This whole layered idea led to a bunch of different specialized networks. You've got CNNs, which are basically the eyes of the AI world, perfect for images. You've got RNNs, the storytellers, built for things that happen in a sequence, like language. And then you've got transformers, the new heavyweights that are masters of understanding language. Now, if there is one single year you need to remember in this whole story, it's 2012. This was the moment the AI winter officially ended with a bang. This was the year that deep learning showed the world what it could do. In 2012, a deep CNN called AlexNet entered a big competition. And thanks to huge amounts of data and powerful new computer chips, it didn't just win, it absolutely demolished the competition. Look at that difference. Its error rate wasn't just a little better, it was a quantum leap forward. This was the moment everyone realized the game had completely and forever changed. So after this whole journey, from copying a single neuron, surviving a brutal winter, and kicking off a revolution, where are we now? Where has this idea of building a digital brain actually taken us? The short answer? Everywhere. These networks are the invisible engines that power so much of our world. They're helping doctors find diseases earlier, they're spotting fraud for your bank, they're powering the chatbots you talk to, they're the eyes in self-driving cars, and they're even creating unbelievable art and music from just a few words. You know, the journey from one tiny neuron to a global artificial intelligence is one of the biggest stories of our time. And as these systems get smarter and smarter, it leaves us with this one really fascinating question. After all this effort we spent trying to make them think like us, what will they end up teaching us about ourselves?